Okay. Yeah, so I am going to talk about Teichmuller space with Teichmuller metric, and it's a Thurston compactification by projectivized measured foliations. So I won't define any of these. So assuming that you have all learned all of that in the past 2 weeks. So, but if you have questions, please. Okay, so I'm going to take a oriented surface. Of genus G. With n punctures. And so I'm going to exclude some of the low complexity cases. So okay, and so I am going to work with a Teichmuller space equipped with the Teichmuller metric. So we know that it's a complete metric space, which is uniquely geodesic. So between any 2 points, there is a unique geodesic. And geodesics have a very nice description. So I will give an example later, so in case you have never seen this. So and so it is known that it is so Masur and Masur with Wolf show that, so it is not delta hyperbolic and it is not cat 0. So, and the space has properties of being positively curved and being negatively curved also. So, and so there is a Thurston compactification. So Thurston showed that so by embedding Teichmuller space and the space of projectivized measured foliations, so in some large space, so he showed that the image is a closed ball. Is homomorphic to a closed ball in R6G minus 6 plus 2n. Okay, and then so here PMF, these are the projectivized measured foliations. And that's there, it's a sphere. Okay, so maybe it makes sense to say what it means for just for a sequence in Teichmuller space to converge to a projective measured foliation. So if I take a sequence in Teichmuller space, so it converges to a measured foliation. So I'm going to write it like that. So that's the projective class of foliation F with a transverse measure mu. If the So given any two curves, simple closed curves, alpha and beta. So Teichmuller space, so you know that it is, one can think of it as a space of Riemann surfaces, some equivalence classes of marked Riemann surfaces, homomorphic to S. Or by uniformization theorem, one can also think of it as a space of hyperbolic surfaces. Okay, so for any Riemann surface, you have a Riemann surface, you have a unique hyperbolic metric, so curvature -1. So here I can measure the hyperbolic length of curves. So I'm going to write it like that. So by this I mean the length of the unique geodesic in the hyperbolic metric of xn. So this converges too. And here, so I can pick any representative of the foliation in the class projective class of f mu. And here, so we have this measure mu on f. So one can talk about the intersection number of a curve with a foliation. And here one means just so one integrates along alpha mu. Okay, so that's what this means. And this is beta here. Yeah. And so one has to make sure that these numbers are not zero, both of them. So it doesn't make much sense. Okay, so the question that I work on from time to time is the following. So given a Teichmuller array, Teichmuller geodesic ray, how does it behave with respect to the boundary? So, so I don't want to say much about what is a Teichmuller array, but so I will first tell you that Teichmuller array is defined by a pair of two objects. So one is a point Teichmuller space. So array defined by there are two things. So a point, so the base point, clearly, and a measured foliation. And so, okay. Okay, so there will be an example later. So so the behavior of array depends on that. So mostly also on the measured foliation. So there is an old theorem of Howard Masur. He tells us so that if this foliation is uniquely ergodic, then the array, let me denote it like this, it's T. The array converges in PMF to the class of this foliation. And so that's one. And another one is the, so if, well, I'm going to call it like that. So if the vertical, if the foliation is a cylinder decomposition, so if one cuts along the critical leaves, then one gets a bunch of cylinders. I call it cylinder decomposition. Okay. So so let's write it like that, so that F mu is by abusing notation, so I will write it as a sum of some coefficient times a curve. Okay. So if it's something like this, so you have your foliation is such that every closed leaf is homotopic to one of the curves alpha I, and so there are weights on them. Okay, so if the foliation is like that, then it's the the height. So it's the width. Yeah, you can also depends on how you put the cylinder, I guess. So that's so it's you have to maybe like normalize. So that's the. Okay, so then the array also converges to so topologically it is the same foliation, but the weights are all the same. So I'll write it like that. So okay, and then so that was like in sorry, I don't know any dates. Maybe late 70s or early 80s. So then so I also proved in my thesis then that there exists a Teichmuller geodesic ray that does not have that does not converge in BMF.
This Mason's theorem do not include all the case because maybe some cylinder and some mixed part.
Right. So you don't even have to have cylinders. So you can have a foliation which is minimal, but not uniquely ergodic. So there are several ergodic measures. So okay, so this is not here. Or you can have cylinders, or you can have just not minimal. Okay, so there will be a picture later. Okay, I just don't want to draw it several times. So okay, and then so one can talk therefore about about a limit set of the Teichmuller array. So just a set of accumulation points in PMF. So set of limit set. And so in this particular case, it was a segment. So one-dimensional was a. Okay. So I don't give more details about this, mainly because I'm going to state a theorem which sort of includes that. So the theorem I want to talk about is so it's a joint work with Babak Modami and Rafi. So, okay, which we'll state as follows. So for any D, there is a Teichmuller geodesic ray and just to not confuse anybody, so in the Teichmuller space of a surface of genus D+1, okay, such that the limit set of that ray is d-dimensional. Okay, so that's the theorem I would like to sketch more or less, and so then if I have time, I will mention other things.
D-dimensional simplex or d-dimensional?
Yeah. Well, d-dimensional simplex is d-dimensional, right?
So it is a simplex, not just.
It is a simplex, yes. You can write simplex, yeah. So one needs to say what the simplex is, so I will. Yeah.
Are you saying that you can go to genus but only to genus -1?
Yeah, so I think that one can improve that. So, yeah. I don't know how much, well, yeah, so how much. So one can try to improve that. So,
I'm sorry, then why you said limited is a segment? What do you mean by
so can I just write? You will understand. So, how do I leave this?
There's a black button.
The black button.
Top one.
The top one. Okay. Okay, so I want to sketch the proof of that, and so I will. Okay, so let me draw you a picture. So you'll take so the construction is similar to the theorem in my thesis. So so you take D+1 unit squares. Okay, and so you are going to, okay, probably most of you have seen this picture millions of times. So the unit squares, and then, so I'm going to so eventually glue the opposite sides of these squares. But so eventually, yeah. But I also will choose so let me put this. Let me call them Ti, the squares. Okay, and then I'm also going to take some so d plus 1. So I will need irrational numbers, and I'm going to pick some number which is small enough. It doesn't matter very much, and I'm going to draw a segment of slope theta I of the same size, of size s. Okay, and then so I'm going to rotate each of the squares so that the segment becomes vertical. Okay, and so the idea is that to glue in the following way. So I'm going to call this side. So I'm going to cut along each of the segments. And so I am going to glue the plus side of T1 to the minus side of T2. Then the plus of T2 to the minus of T3, and so on. Okay. And the last one, so I'm going to glue the plus of TD plus 1 to the minus of T1. Okay. And so as I said, I'm also gluing the opposite sides of the tori. And what I get is a surface of genus D plus 1. Okay, so you have the. So what also you get is so like I said that the Thurston the Teichmuller array is defined by a vertical foliation, by a measured foliation. Sorry, so the measured foliation is the vertical foliation that you see here. So just take that's the vertical foliation, and the measure is just the dx. Okay. So I have and since I took the theta I irrational, so you can already see that. So you will have like the vertical foliation is going to be dense, like restricted to each of the pieces. It's going to be dense there, okay? Because the slope I took is irrational. Okay, and so I get a surface X of genus G, genus D plus 1. And then I get this vertical foliation, the vertical foliation. Okay, and what I'm going to do, I'm going to call so probably not very correct to write this, but I'm going to define nu I like this. So it's the mu restricted to Ti. Okay. So just put 0 on everybody else, and just take the measure here. Okay. So the theorem that one proves is that there exists these irrational numbers that one can find these d+1 irrational numbers such that the corresponding Teichmuller array such that, the limit set is the following. So it is just the simplex defined by the simplex spanned by the classes of F nu. Okay, so these are all right, like that. So it's F, and the measure is sum of Ci nu I Okay, so you can ask the and I take the projective class. So I projectivize. Okay. So if D is 1, then so that's so actually in my thesis I did not prove that it is one simplex. So I proved that it is more than 1 point. If it is more than 1 point, a limit set has to be connected, so it is automatically a segment.
Are there any other geodesics also the limit set of that other geodesic included in this limit set?
I don't. So are there?
This is the limit set of one geodesic. Then are there any other geodesics also have the limit set as this?
Well, yeah. I mean, you can take another. Yeah, I don't know if you change the base point. I never thought. Yeah. So, yeah, I imagine that yes, that you can. Yeah, I don't know. Yeah, I have not thought of that. Okay, so and what is the maybe like I should say briefly. So how does one get the Teichmuller array from this picture? So for each t. Okay, so one applies the following map. So one applies. So I'll just write it like that. So xt is the okay. So you just expand horizontally and contract vertically, and that gives you a new Riemann surface, so a new structure. Okay, so so just imagine, so taking this picture and just expanding horizontally and contracting vertically. So in particular, you will see that these segments, the length of these segments that are in this picture here, okay, so they all go to 0. So what you get is a kind of, so this kind of more and more independent tori, okay, because these curves shrink, and so what you get is basically d+1 tori, and in a torus it's kind of much easier to do computations. So that's
Those 5 short curves are closed curves, but the one that you draw the vertical direction, that's a infinite, that's a free. That's a free, right? The vertical direction.
a geodesic.
Oh no, I mean that's not a closed, that's not a single closed curve. But that's a single closed curve. How can that goes to 0?
So, well, okay. So do you understand? So here I cut here, right? Here, and here. Okay, and so I glue. So here there's a cut. So I glue this side to this side. So if you just do it with 2, it's easier to see. If you do it with two things. Okay, so here you just pull them like that, and you have a surface of genus 2. Okay. Okay. So okay, so I want to sketch a proof of that, and so what is the difficulty here in general in this kind of question is that, so here we have the data we have is so we have this flat metric, okay, and then so by applying this map, we know how this flat metric gets deformed, okay, so you can take any curve, especially in the torus, and just compute its flat length easily, okay. So the game is to, but as I said, the Thurston compactification is using hyperbolic structure, and so one does not know, one cannot precisely go, well, cannot, at least, so from between a hyperbolic, from flat structure to hyperbolic structure. Okay, so one has to approximate and stuff like that. Okay, so what do I want to do? Is so I want to sketch the proof of this theorem. The theorem is a fault. So what I want is first fix a countable set. Of triples of integers, of actually natural numbers. Okay, such that if I consider them as points in the PR3 plus, so I get a dense set. Something like that. Okay. And so what I want is to find a sequence of, so I want to, Y3 because I decided that D is 2. Okay. It's much easier to write. Sorry about that. Okay, so D is 2 from now on, and the proof is not very different. Okay, for D bigger than 2. So what I want is to prove that so there is a sequence of times so I want to find theta 1, theta 2, theta 3 such that there is a sequence of times that goes to infinity such that for any two curves, gamma and gamma prime, simple closed curves on S, the ratio of hyperbolic lengths is coequivalent, so meaning that so the ratio goes to 1 is the sum 3, and here I have this u I n, and here I have intersection of gamma with f nu I, and same divided by same with gamma prime. Okay, so I want that these theta 1, theta 2, and theta 3 give me this. Okay, so the question is how does one compute hyperbolic length? So okay. Or compute meaning, well, approximately. Okay, so in general, the tools we have is by using short curves, by figuring out what the short curves are and using short curves. So more precisely. So I draw you let's say this is an annulus. The core curve is short, let's say very short. Okay, so let's say here the length is 1, and here the length is 1. Okay, so this is in the hyperbolic metric. So the width of this annulus, I call it the width of alpha, and so basically we know by Kohler lemma that it is up to bounded additive error logarithm of 1 over the hyperbolic length of alpha. Okay, so that's just the Kohler lemma that gives you that. And okay, so that's very good. And then, so imagine there is a curve that crosses alpha, maybe many times, probably many times. But let's look at just one arc. So so let's say you have a geodesic. So of course I'm talking about geodesics. So gamma, what does it do? So it comes here. It maybe twists some amount of time, and then. So sorry, this was 2 here. Okay, so here's my curve gamma. And so approximately the length of this arc, just restricted to this color, is the width, because it has to go all the way, plus the length of so every time it twists around alpha, you have to add the length of alpha. So it's the number of times gamma twists around alpha times the length of alpha. Okay, so one defines the following thing, definition. So hyperbolic. So this is a contribution of alpha to the length of gamma. So this is just defined as the width of alpha plus the length of alpha and multiplied by the number of times gamma twists, the twist of gamma around alpha. Okay, and all of this has to be multiplied by the number of times gamma and alpha intersect. Okay, so of course, so gamma is a simple geodesic, so closed geodesic, so every such arc is going to do about the same thing. Okay. Okay. And so I'm going to go here. Yeah.
Each time they intersect, the gamma loop is the same amount of times.
Yeah. Well, yeah. So there is maybe some error, but yeah. Okay, and so there's a theorem of, I think, Choi, Rafi, and series, I think maybe 2007, that says that, so if, so let's say, so X is a hyperbolic surface, or point, let's say, point in Teichmuller space, and we take P, so it's a short Pence decomposition. Okay, so just this decomposition of the, so this is a multi-curve that decomposes the surface into a pair of Pence, and the curves one takes are the shortest possible. Okay, so to get one, you take the systole, and then the next shortest, and so on. Okay, that gives you short Pence decomposition. So then the hyperbolic length, so for any simple closed curve gamma, well, geodesic, of course. So the hyperbolic length, so of gamma minus, and then I take all the contributions to the length of gamma from the curves in the short Pence decomposition. So that this is bounded by some constant that I think so. It depends only on the topology of the surface. Times the intersection number of of gamma with alpha, for all alpha in the short Pence decomposition. Okay, so the error is can be big. Okay, so but if the length was so much bigger, so then it's yeah. So yeah.
So this works only for short Pence decomposition, and by short sum of the lengths or maximum of the lengths, or
Yeah, I think you can define it like that. So the
For the sum of the length.
for the sum of the length is minimal. Yeah, I think you can define it like that. I mean, if you have like your surface has like only has a lot of short curves, and you don't have much choice. So because anybody crossing a very short curve is very long. So okay, so that's the that's what we want to do. So okay, so now we think again about the ray, which I have. So I'm gonna draw the picture again for the case d equal to 2. So let's call it this T1, T2, T3. Okay. So what are short curves? So there are three curves, three dividing curves, which are homotopic to the union of some of the slits, yeah? So let's call them beta 1. This is beta 3, beta 2. Okay, so there are these curves beta I. Okay. So the length of beta I go to 0 along the ray. Okay, so and then so that means that we only look in the tori. So in the tori, so let's say in T1, okay. So remember that the slit was of direction of slope theta 1. Okay, so now I look at the continued fraction expansion of theta 1. Let's call it A0, 1, maybe the other way around, 1. And so on. And so, so you know that if you go until n, coefficient n, and then you look at the corresponding rational number, that's called convergent of theta 1. So for any t, so it's a fact for any t, the shortest curve on T1 is, so I'm going to call it alpha 1n, like that. So it's of the slope equal to 1 of the convergence of theta 1. Okay, so convergent again, so you take first n plus 1 coefficients, and that gives you a rational number, and it's that. Okay. So the computation you do it for the flat metric. Actually, the flat metric computation gives you that. And then yeah, so you can go via extremal length and then hyperbolic length. So it's kind of like that. And then, so moreover, So of course that so n depends on t, and as t goes to infinity, n goes to infinity too. Okay. So moreover, we know the minimum of the hyperbolic length of such curve. So the minimum is up to multiplicative error 1 over a n plus 1. So the coefficients of so the minimum has something to do with the coefficients of in the expansion of the slopes. So it tells you that, well, if you want that you have very short curves, you need to take coefficients very large of the slopes theta I. And then we also know exactly when, well, not exactly, but up to some bounded error, we know when that minimum happens. Know that the hyperbolic length of such a curve is minimal roughly when that curve is balanced. So balanced is in terms of flat metric again. So there is a notion of horizontal length and vertical length. Vertical length goes to infinity. Horizontal length, no, the other way around. Horizontal length goes to infinity. Vertical length goes to 0. At some point, they are equal, and that's the balance point. Okay. So it doesn't. Yeah. So, but we know. So I won't write. We know when that happens. Okay. So. So the problem is that most things we know are with multiplicative error. So if you want to say that, well, you're along some sequence, or your array approaches this point, at this point, at this point, at this point, you cannot really do that if your estimates of short curves are with multiplicative errors. Okay, so the only time when the error is okay is when so the problem is multiplicative errors okay. So but so let's say if a n plus 1 is these coefficients is very, very big, and this alpha, the curve alpha is close to being balanced, then so basically and then okay, just believe me, everything that basically the contribution of such a curve to a curve that crosses it is just the width. Okay, so the twisting, how much it twists, it doesn't matter because it's just so short. Okay, so what matters is just the width. Okay, and the width is with the logarithm of 1 over hyperbolic length. And then if we know the hyperbolic length up to multiplicative error, if you take the log kills the multiplicative error, and you have some small additive error that you can control. And that's the point of the whole thing. So, okay. So Right. So let me write it like this. So the hyperbolic length, the contribution to any curve gamma of such a curve is roughly, so the intersection number times the log of an plus 1. Okay. We also know, and that's again like a high school computation, that the intersection, this intersection number of alpha and 1, because it's a concrete curve, so you know what it is. So it is asymptotically the same as, okay, I am in big trouble. So this, here you have this Qn1, okay, very good. So you have Qn1 times the intersection of actually nu 1 with gamma. Okay, so let me just summarize everything. So long story short, right? So here I wanted also to say I'm completely out of time. So okay, so you have for genus 2, genus 3, you have so 6 short curves, right? So you always have these curves beta 1, 2, 3. Okay, we know that the length goes to 0, and you also in each tori you know what's going on. So you have these 6 curves in the short Franz decomposition, so you can estimate the length. And another thing, so to point out, and again it's a computation, is that the hyperbolic length of beta I does not contribute very much to the length of anybody crossing it compared to what happens in the torus, because the hyperbolic length goes to 0, but not fast enough. So the color, the width is not that big. Okay, so it's like and then also these are the same curves, so they are the same curves, so the intersection with these curves does not change. Like you take your curve gamma, so the intersection with beta 1, beta 2, beta 3 is some constants. Okay, so the only thing that happens is that the color grows slowly. But here, as you can see, the intersection of gamma with alpha, with the curves alpha, and so that grows fast. That grows exponentially. Okay, so right. Okay, maybe that's yeah. Maybe I should stop here. Yeah, I'm completely out of time. Yeah. So basically, the point is to manipulate the situation. Manipulate the situation so that so I have these 3 tori so that the curves alpha and 1, alpha and 2, and alpha and 3 get short at the same time, get balanced at the same time, so they are at minimal length at the same time. Okay, and so that their width are, of course, they are very different, but they are so big that the ratios go to 1. So the widths of alpha n are all about the same at the time when they're, of course, smallest. Okay, and so that's the it's kind of technical. So, but okay. So the idea is to choose your coefficients for these theta i's so that this happens, and then you get what you want. Okay. So sorry.